Now let us learn about some more terms related to coordination complexes. Coordination polyhedron. When ligand atoms, molecules or ions surround the central metal or ion, they impart a particular geometry to the complex. This is called as coordination polyhedron. Examples of such spatial arrangements include tetrahedral, octahedral and square planar geometry. Usually, when the coordination number is 4, we see commonly tetrahedral and square planar complexes. And if the coordination number is equal to 6, then octahedral geometry is seen. Oxidation number. The oxidation number of the central atom can be calculated by finding the charge associated with it when all the electron pairs that are donated by the ligands are removed from it. For example, the oxidation number of platinum in complex PtCl taken 6 times 2 minus is plus 4. Let us see how it is calculated. The oxidation state of isothiocyanate ion is -1 and that of ammonia is 0 and sulfite ion is -2. Now let the oxidation state of cobalt be X. Then just as we calculate the oxidation state of any atom in case of a simple ordinary compound, the same way the element whose ever oxidation state is to be calculated, we assume it is as X and then we sum up the oxidation states or charges possessed by the other groups or atoms that are present in the compound. The same way we are going to calculate the oxidation state of cobalt. Let the oxidation state of cobalt be X, then X plus one group of isothiocyanate ion is present multiplied by its charge -1 plus 5 ammonia molecules are present with each possessing a charge of 0 plus 1 sulfite ion is present with a charge of -2. If you simplify this, we get X minus 1 plus 5 is equal to plus 2. And when you simplify the value of X, when you calculate the value of X, we get X is equal to plus 3. Therefore, the oxidation state of cobalt is plus 3. Now you see this complex of cobalt. Here we are assuming the oxidation state of cobalt to be X, then X plus we have 4 molecules of ammonia each possessing a charge of 0 on it. So 4 into 0 plus we have 2 chloride ions each having a charge of -1. So 2 into -1 is equal to, if you remove the sulfate ion, the net charge possessed on the coordination sphere is equal to plus 2. So equate it to plus 2. Then X minus 2 is equal to plus 2 and X is equal to 4. Thus we calculate the oxidation state of central metal atom using this method. Now let us see how coordination complexes are classified. They are classified in different ways based on various aspects. So now let us see how they are classified based on whether the complex ion is a cation or anion. Cationic complexes. As the name tells you, it is clear that in a cationic complex, the coordination sphere has a positive charge. That means the coordination sphere is a cation. Such complexes are called as cationic complexes. and the complexes in which the coordination sphere is a anion possessing a negative charge, then it is called as an anionic complex. And if the complex possesses no charge on it, if it is neutral, then it is called as a neutral complex. Examples of cationic complex is CONH3 taken 6 times Cl3. Here you can see CONH3 taken 6 times. This complex has a charge of +3. So it is positively charged. So it is a cationic complex. When we look at the next example, potassium hexacyanoferrate ion, potassium hexacyanoferrate complex, we see that potassium ion possesses a positive charge on it. So the complex acquires a negative charge of -4 on it. Because the coordination sphere possesses a negative charge on it, it is called as a anionic complex. NiCO4 possesses 0 charge on it. You don't find any charge on this complex. So it is a neutral complex. You can also classify complexes based on the central atoms or ions present in it. Based on the number of central atoms or ions present in it. For example, mononuclear complexes. In this coordination sphere, if you consider the example of potassium hexacyanoferrate, the complex contains only one central metal atom. So what is the central metal atom in this complex? It is iron atom. And how many iron atoms are present in this complex? Only one iron atom. So you can say that it is a mononuclear complex. Now you observe this complex. Here in this complex you can see there are two central metal atoms, and therefore this is called as a polynuclear complex. So what is the basic difference between a mononuclear complex and a polynuclear complex? In a mononuclear complex, there is only one single central metal ion or atom. But whereas in case of a polynuclear complex, you can see there are two or more metals in the complex. Now let us see how complexes are classified based on the types of ligands present. They are broadly classified into homoleptic complexes and heteroleptic complexes. What are homoleptic complexes? Homo means same. So if a complex possesses only one kind of ligand, atoms, ions or molecules, then it is called as a homoleptic complex. For example, in potassium hexacyanoferrate complex, there is only one type of ligand present. Only Cn- is the ligand present, and that is why it is called as a homoleptic complex. If you observe this complex of CONH3 taken 5 times ClSO4, you can see there are two types of ligands. Ammonia and chloride ions are the two types of ligands present. So the complexes in which there are different types of ligands present are called as heteroleptic complexes. Hetero means different. So because different types of ligands are present in this complex, it is called as a heteroleptic complex. With this, we have learned almost the most important terms we come across in coordination compounds. Now we will enter into the deeper part of coordination complexes with the knowledge of the terms we have acquired so far. Thank you.